Welcome back to the Radicals chapter of Organic Chemistry. In this episode, we're going to explain something you've likely learned in your first semester of Organic Chemistry, which was anti-markovnikov bromination of an alkene, or hydrohalogenation, I should say. So, just for a refresher, let's go back. We have an alkene here, and it's reacting with hydrobromic acid. What do we expect the product to be? Well, remember, Markovnikov's rule is going to state this bromine here is going to go on the more substituted side. Remember, the mechanism goes like this. Roughly, the H will add to this side, leaving a carbocation on the secondary carbon, and then Br comes in, attacks that center, and we get our final product, which is a bromine that follows Markovnikov's rule. And remember, Markovnikov's rule says add to the more substituted side. Well, remember this reaction, maybe you didn't. Maybe you didn't even cover this yet. But if we have hydrobromic acid, but then we throw in H2O2 and some heat, what's going to happen? Well, you're probably just told the reaction mechanism here. You probably weren't shown it. And that's because it's a radical mechanism, and it follows like so. You get this product, and it's not following Markovnikov's rule, it follows anti-Markovnikov's rule. So Markovnikov, he's sad. He's very sad. Makes him sad. Anyways, let's get into the mechanism here. What about it? What about H2O2 is going to cause this anti-Markovnikov addition? Well, again, it starts with initiation. We know peroxides are good at becoming radical. They're pretty radical, but they go like this under heat or photochemical conditions. We get a splitting, and we get two peroxide radicals. Now, propagation occurs next. Propagation is a non-radical species with a radical species, and then they kind of swap, right? That non-radical species becomes radical, and the radical species becomes non-radical. So it first starts with an equivalent of hydrobromic acid, and we're going to react it with the radical species of OH. Now, we get a coupling, and bromine radical gets formed. I'm just going to write minus H2O because it's not important anymore, but as our major product going forward, it's going to be a bromine radical. Now, what happens next? Now let's bring over our alkene. So for this step of propagation, our non-radical species is the alkene, and we'll say bromine is our radical. And now we're going to homolytically cleave the bond. Now, before I show where the one radical electron will go, let's just couple these two together. So where do you think the next radical electron of this pi bond will go? Will it go on a primary carbon or a secondary one? Well, if you said a secondary, you'd be correct, right? Because it follows the same trend as carbocation stability. It's going to be more stable on the more substituted carbon, and that's due to hyperconjugation, that ability for those electrons to spread out between those orbitals from the carbon atoms. So what we get is we get this here, and we get a radical electron on that carbon. So what occurs next? Well, another propagation step. There's actually three here of importance. And we come in with another equivalent of hydrobromic acid. We have a radical electron here. It's going to couple with a hydrogen through radical means, and then bromine gets to become radical. So we get our intended product here that we've shown here, but we didn't specify the mechanism, and then we get a bromine radical as a byproduct. And this bromine radical can come up here and do the exact same thing all over again. So that is the anti-Markovnikov hydrobromation of an alkene, and I hope you guys enjoyed.